Welcome to the Deep Dive. We're all about taking those sources you've given us and pulling out the really key stuff so you can get up to speed quickly. And today, we're going to be diving deep into this chapter on knowledge representation.
That's right.
This is all about how we can capture what we know about the world so that computers can understand it.
Yeah, exactly. So our goal in this deep dive is going to be to unpack how we represent that knowledge about the real world
Right?
so that machines can then reason about it and use it to solve problems.
Mm.
We're going to start with a look at first-order logic, which is sort of a fundamental tool here.
Right.
It uses predicates to describe objects and then quantifiers like all and some to make general statements. But we'll also be exploring some other interesting approaches along the way.
Yeah, I'm excited to get into this. We're going to be talking about organizing this knowledge using things called ontologies, which are essentially like frameworks for representing concepts, as well as how we represent categories of things and individual objects.
Yeah.
We're also going to tackle how we deal with time and events,
Yeah.
and even touch on how we might represent beliefs.
Yeah, it's going to be a really comprehensive deep dive.
Okay, so let's dive right in, starting with ontological engineering. So what is the big idea behind ontological engineering?
So in essence, ontological engineering is all about creating general and adaptable ways to represent concepts like events, time, physical objects, and beliefs. So these sorts of things that we see across all different fields. It's sort of like a foundational blueprint, but the real difficulty lies in building these very broad structures to encompass all types of knowledge. How do you even begin to decide what the most fundamental concepts are, and how do you get everyone to agree? It's a huge theoretical challenge.
Yeah, our source actually uses this helpful analogy of comparing it to an object-oriented programming framework,
Right.
like Java Swing. So you have, these general concepts like window,
Right.
and then developers can build more specific things like spreadsheet window on top of that.
Absolutely, and that's exactly how it works in knowledge representation. You have this, in general, framework of concepts that we call an upper ontology. So the idea is to have these very broad categories at the top, like anything.
Right.
And then it branches down into more specific concepts. So anything might split into abstract objects and physical objects.
Oh.
And then further down, you have things like humans, animals, and times, and so on. It's illustrated really nicely in figure 10.1 in your chapter.
Yeah, that's a really helpful visual. Now, the source does mention right off the bat that first-order logic, which we're kind of starting with,
Yeah.
that it has some limitations. What would you say is like a key challenge it faces when trying to represent, that messiness of real-world knowledge?
Well, the biggest hurdle is definitely dealing with exceptions and uncertainty, which are like just so fundamental to the real world. Take the example, tomatoes are red.
Right.
That's generally true, but of course we all know there are green tomatoes, yellow tomatoes, orange tomatoes.
Right, exactly.
First-order logic really prefers those clean, universally true rules. And that just clashes with the reality that there are often exceptions. And our source does mention that, handling these is important, but it will be discussed a little bit later.
Okay, so even with this, inherent tension, I guess,
Yeah.
between those logical rules and the real world, why even bother creating an upper ontology? What's the practical advantage of doing that?
Well, if you think back to the circuit ontology that was mentioned in section 8.4.2, it made some pretty significant simplifications, right? Time was ignored, signals were static, and the circuit structure was constant. A more general ontology, on the other hand, wouldn't have those limitations.
Right.
It could actually represent signals changing over time, so you can account for things like wire lengths and signal delays.
Okay.
This could lead to some really useful, more realistic simulations for circuit designers.
That's really interesting. And they actually take this even further and say, what if we wanted to think about different kinds of logic gates or even like how reliable the circuit is?
Absolutely. So a more general ontology, it could actually describe different gate technologies, things like TTL and CMOS, with their very specific input-output characteristics.
Okay.
And if you want to analyze reliability or even diagnose faults, you would need to be able to represent the fact that maybe the structure of the circuit could change or components could malfunction. And even things like stray capacitances, to model those, you would need to represent the physical layout of the wires and how they're all arranged.
That makes sense.
Yeah.
And then they even tie this back to the Wumpus world, which is, that classic AI problem.
Yeah, they do. So the Wumpus world, it has a very basic notion of time.
Right.
It's very simplified. Changes only happen when the agent acts, and they're instantaneous. But a more general ontology could actually handle simultaneous events unfolding over time. So, instead of just having a generic pit predicate, you could have different types of pits with, varying degrees of danger, or you could even have a biological taxonomy for different creatures in the cave, so that the agent can make inferences based on limited information.
Right. Right. It's like as we go from, these simple environments like the Wumpus world to the real world,
Yeah.
it gets so much more
Right.
complex. It makes you wonder, are all these specialized ways of representing knowledge ultimately aiming for one big unified system?
Yeah. So that leads to a pretty fundamental question, right? Do all these specific ontologies that we build eventually converge on one single general purpose ontology?
Hmm.
And the answer, even after much debate, is kind of a maybe.
Yeah.
Our source actually highlights two key characteristics that you want to see in these general purpose ontologies.
Okay.
So first, they should ideally be applicable to almost any specific domain simply by adding more domain-specific details. So, you can't really sidestep the fundamental representational challenges. And second, in complex areas, you need to be able to integrate different kinds of knowledge. So they use that example of, a robot repairing a circuit, which is perfect, right? It needs to reason about electrical connections, physical layout, and time all at once.
Yeah, I mean, it sounds incredibly ambitious.
Yeah.
Has it been like a major success story in AI so far?
So our source actually points out that despite all the effort that has gone into it, general ontological engineering hasn't really been the driving force behind some of the most successful AI applications we see today.
Okay.
Most current AI really relies on more focused, special purpose knowledge engineering and, increasingly just machine learning techniques.
Mm-hmm.
So the dream is there, right? That universal ontology. But right now, it seems like AI is taking a bit of a different path.
There's even social and agreement-based challenges involved in this, right?
Oh, absolutely. Tom Gruber, he actually has this quote where he says that ontologies are treaties.
Which really captures it, right? Because getting everyone to agree on these fundamental concepts,
Right.
especially across different groups that may have very different perspectives, is just incredibly difficult. And that's why building a general purpose ontology is so much harder than just building one for a very specific, limited domain.
That makes sense. So if these big, unified ontologies are so hard to create, how have the ones that actually do exist been developed?
Well, the source outlines 4 main approaches. Okay. So the first one is the traditional method, which is basically a dedicated team of ontologists and logicians carefully designing the structure and writing all the logical rules like the CYC system.
Right.
The second approach is by importing existing structured data from databases. So DBpedia, for example, was created using information from Wikipedia.
Sure.
The third approach involves actually automatically extracting information by parsing text documents, like the text runner system.
And finally, there's this more collaborative, crowdsourced approach. So encouraging volunteers to contribute common sense knowledge, like the Open Mind Project.
And we actually even have a massive real-world example with the Google Knowledge Graph.
Oh, absolutely.
Yeah.
So that uses a combination of semi-structured content from Wikipedia,
Right.
as well as other web data, and it's curated by humans. The scale of it is just immense, right? We're talking over 70 billion facts. And according to, the figure they cite from 2014, it's used to answer about a third of all Google searches.
Wow.
But of course, maintaining something that vast and constantly evolving has its own set of challenges.
For sure. Okay. So we've got this idea of organizing knowledge, but now let's actually get into what we're organizing, which is categories and objects. Why is it so important to group things into categories in the first place?
Well, think about it. A huge amount of our reasoning happens at the level of categories, even when we're interacting with individual objects. So, when you go shopping, you're usually looking for a type of thing, like a basketball. It's
Right.
not necessarily a specific basketball.
Right.
And categories let us make predictions.
Okay.
If we can classify something as belonging to a certain category based on its properties, we can then infer other things about it. The example in the chapter with the watermelon is perfect. So based on its appearance and where you find it, you can infer that it's a watermelon.
Okay.
And from that, you can predict that it would probably be good in a fruit salad.
Right, exactly. And how do we represent these categories within the first order logic framework? The source mentions 2 main ways.
So we can use predicates, so for example, basketball, to say that B is a basketball.
Go.
Or we can reify the category itself, so like basketballs, and then use a membership relation like B basketballs to say that B is a member of that category.
Right.
And we can also, of course, represent subclass relationships like basketball's your balls.
Right. And this leads to that crucial idea of inheritance.
Exactly. So inheritance is all about how categories can help us organize knowledge efficiently. If we know that all members of the food category are edible,
Okay.
and fruit is a subclass of food, and apples are a subclass of fruit,
Right.
then we can infer that all apples are edible. So the apples are inheriting that property through their membership in these increasingly specific categories.
Right. So it creates like a whole structure or hierarchy of knowledge.
Exactly, a taxonomic hierarchy or taxonomy.
Right.
And these have been used, for centuries in fields like biology or library science with the Dewey Decimal System, and even government classifications of occupations and products. And first-order logic gives us the tools to easily express facts within these hierarchies. So, saying that an object is a member of a category, or a category is a subclass of another,
Right.
or all members of a category have certain properties.
Okay. Now, what happens when categories aren't so neatly nested within each other?
Yeah.
What if they overlap or they're completely separate?
Well, our source introduces these concepts of disjoint categories, exhaustive decomposition, and partitions.
Okay.
So 2 or more categories are disjoint if they don't have any members in common.
Okay.
So, for example, animals and vegetables are generally considered disjoint categories.
Right.
And exhaustive decomposition means that a set of categories completely covers a larger category. So, for example, you could say that Americans, Canadians, and Mexicans are an exhaustive decomposition of North Americans.
Right.
And then a partition is a special case where the categories are both disjoint and form an exhaustive decomposition.
Right.
So, in biology, you have the classification of animals, plants, fungi, Protista, and Monera, and together they partition all living things.
Right.
So these distinctions are really important because they allow us to make sure that our reasoning about categories is sound and complete.
And then how do we actually define, what belongs to a category in the first place?
So ideally, we would define categories with necessary and sufficient conditions for membership, like the classic example of a bachelor being an unmarried adult male.
Right.
However, as that sidebar on natural kinds points out, this is often easier for those formal artificial terms than it is for everyday objects like, tomatoes. Natural kinds tend to have fuzzy boundaries and typical features rather than those strict logical definitions.
Okay. Well, let's move on from categories to how things are put together physically, physical composition. And this involves that part-off relation.
Exactly. So the part-off relation just describes how one object can be physically contained within another object. So, a nose being part of a head or a chapter being part of a book. And just like the subset relationship for categories, it also creates these hierarchies. And importantly, part of this is transitive. So, if A is part of B and B is part of C, then A is also part of C. And it's also reflexive, meaning that everything is part of itself.
Okay. What about, more complex objects that are made of multiple parts, but they also have to be arranged in a specific way?
So those are composite objects.
Okay.
And our source uses the example of a biped, which is defined as having exactly 2 legs attached to a body.
Right.
But representing that exactly 2 constraint in first-order logic is a bit tricky.
Okay.
It requires us to say that there are 2 legs, they're distinct, and any other leg must be one of those 2. It gets a bit cumbersome. The source mentions that description logics, which we'll talk about later, offer a more elegant way to express those sorts of constraints.
Okay. And then there's this idea of a bunch, like a bunch of apples.
Right.
So how is that different from just a set of apples?
So that's an important distinction because a set of apples is really just an abstract mathematical concept. It has elements, but it doesn't have physical properties.
Okay.
So you can't say a set of apples weighs 2 pounds.
Right.
But a bunch, as defined here, is actually a single object made up of those apples as parts. So the bunch of apples in the bag, that can weigh 2 pounds. The source even gives a logical definition of bunch-off using the part-of relation and this idea of logical minimization, which we won't get into right now.
Okay. So moving on, let's talk about how we actually describe the characteristics of objects, measurements. And it's not just about saying something is big or small, is it?
No, it's much more precise than that. Measurements are really the values that we assign to properties, things like height, mass, or cost. And the source introduces this idea of measure objects and a units function. So, for instance, the length of something can be expressed as inches, 1.5, or centimeters, 3.81, both referring to the same underlying length.
Okay.
And then unit conversion becomes a matter of equating different multiples of those units.
Okay, so like $19 represents a price, not like a physical dollar bill itself.
Exactly.
Okay. And even like zero measurements can be a little bit tricky.
Yeah, so while inches, 0, and centimeters both represent zero length, we're not actually identical to other zero measures like seconds. They're different types of measures.
Right. That's interesting. What about qualities that don't have like universally agreed upon scales, like how difficult an exercise is,
Right.
or how delicious a dessert is? Can we still reason about those?
Yes, we can. And our source makes the point that the most important aspect of these measures is not always the numerical value, but the fact that they can often be ordered.
No.
So even without assigning a precise number to the difficulty, we might know that exercise A is harder than exercise B.
Right.
And this ordering allows us to make inferences, like deciding which exercise to do based on their relative difficulty. And this is actually a fundamental idea in what's called qualitative physics, which tries to reason about physical systems without relying on detailed numerical equations.
That makes sense. Okay, then we get into the slightly more philosophical distinction between things and stuff. So what's the core difference there?
So the fundamental difference lies in how easily we can individuate them, meaning count them as distinct individuals.
Okay.
So things like an aardvark are pretty easy to individuate, right? You can have one aardvark, two aardvarks, and so on.
Right.
But stuff like butter or water, it doesn't really lend itself to that easy counting because any portion of it is still considered stuff.
Right.
And English actually reflects this with the distinction between count nouns and mass nouns.
Okay.
So how do we represent stuff in our knowledge representation systems? Well, one way is to recognize like those gross lumps of stuff as individual objects. So, butter 3, referring to that specific pat of butter on the table. And then we define a category butter, where any part of a butter object is also considered a butter object. And this helps us represent those properties of the substance itself, like its melting point, which would apply to any instance of butter. Importantly, stuff doesn't have a size, shape, or weight.
Right.
Those are all extrinsic properties.
And that connects to the idea of intrinsic versus extrinsic properties.
Exactly. Intrinsic properties are inherent to the substance itself,
Okay.
like its density or its color, and they don't change when you divide it.
Okay.
Extrinsic properties like weight or shape, those belong to the object as a whole,
Right.
and they change if you divide the object.
Right.
So substance nouns or mass nouns, they describe things primarily based on those intrinsic properties, but count nouns can include both intrinsic and extrinsic properties.
Okay. That makes sense. So we've talked about objects, the properties, but now let's move on to the things that happen, events.
Right.
How does this idea of event calculus provide a more, I guess, sophisticated way of thinking about actions compared to the simpler models that we talked about before?
Yeah, so event calculus gives us a much richer framework for representing those events in the real world. And it goes beyond just simple instantaneous actions.
Okay.
So you can handle things like continuous actions, like filling a bathtub over time, or simultaneous events like brushing your teeth while the bathtub is filling. And the core idea is to actually treat events, fluents. Those are things that are true or false at a given time,
Right.
and time points as objects in our logical framework.
Okay, so instead of just saying shoot happened, we can reify the event, treat it as an object, and then add like all these details about it.
Exactly. So you can have an object representing, say, a specific flying event, E1,
Okay.
and then you can associate all these properties with it, like, who was the flyer, the origin and destination, maybe even whether it was bumpy or not. And this ability to attach, arbitrary information to an event is a real advantage over just using inary predicates,
Right.
where the number of arguments is fixed.
Okay, so the source lists a bunch of these key predicates in event calculus, things like happens, initiates, terminates. What do these tell us about how events actually affect the world?
So these predicates basically allow us to formally describe how events change the truth of fluence over time. Okay.
So happens E T1, T2 just means that the event occurred between those times T1 and T2. Initiates E FT means that the event caused the fluent F to become true at that time.
Okay.
And conversely, terminates E FT means it caused it to become false. And then there are also these predicates like initiated, and terminated to describe when a fluent became true or false within an interval.
Hmm.
And then, of course, we have our standard less than predicate to order the time points.
Right.
So, imagine a door open event, right?
Yeah.
We could use initiates to say, happens, door open 10:00.
Yeah.
Initiates, door is open true, 10:00. So it's very clearly showing how that event changes the fluent door is open to true at that specific time.
Okay, and we can even describe, like, the initial state of the world using event calculus? We can, yeah. So by using a special start event and then initiates and terminates, we can define which fluents are true or false initially. And then the source goes on to present some axioms for how the truth of a fluent persists over time, kind of similar to the successor state axioms we've seen before, but now it's tied to the specific events that initiate or terminate the fluent.
Right.
It's also worth mentioning that event calculus can actually be extended to handle a lot more complex scenarios, including simultaneous events, external events, continuous events, and even unpredictable events.
Okay. Well, all this discussion of events, it leads us very naturally into the concept of time itself.
Yeah.
So how do we represent specific points in time and durations of time within this framework?
So event calculus really brings the concept of time to the forefront.
Right.
And we can represent time points as moments, which have no duration, and extended periods as intervals. We can then define a time scale. And the source actually does this using seconds from a specific date. And functions like begin, end, time, and duration allow us to work with those time intervals and points. They even provide a date function just for easier readability.
Okay.
And then are there ways to define, like, the relationships between different time intervals?
Yes, definitely.
The source introduces what's called Allen's interval relations, and it gives you a complete set of ways that two time intervals can relate to each other.
Okay.
So you have meet, before, after, during, overlap, where they share some, but not all their duration
Right.
starts, finishes, and equals.
Okay.
And figure 10.2 in your chapter actually visually illustrates these.
Yeah, it's helpful to be able to see it.
Even the overlap relation has a very precise definition here, focusing on that starting point. And these relations let you express things like, one event happening right after another, or two events happening at the same time.
So we've talked about events happening within time, but what about physical objects that exist throughout time?
Yeah.
How do we represent, their persistence?
The source actually suggests this really fascinating perspective, viewing physical objects as these generalized events, chunks of space-time. So take, the USA as an example. It began as 13 states in 1776, and now it exists today as 50 states.
Right.
We can use state fluents, like population USA, to describe those properties that change over time.
Yeah.
But then what about something like President USA, which changes every 4 years?
Right.
That becomes a bit of a logical puzzle because a logical term usually refers to a single unchanging object in a given model.
Right.
So the source clarifies that President USA actually denotes a single enduring object that consists of different people at different times. So, George Washington from 1789 to 1797, then John Adams, and so on.
Okay.
And to express that, George Washington was president throughout 1790, we would use that T fluent and the equals function.
Okay.
To assert that during that time, the object denoted by President USA was equivalent to George Washington.
Okay, so we've explored the physical world, events unfolding in time, but now let's get a little bit more abstract and talk about mental objects and modal logic. So, first, why do we even need to represent beliefs and knowledge in AI?
Well, because truly intelligent agents, they need to be able to reason not just about the external world, but also about their own internal states, their knowledge, their beliefs. And they also need to reason about the knowledge and beliefs of other agents.
Right.
So this is crucial for things like deciding when to stop thinking about a problem and act.
Okay.
And also for understanding the intentions and capabilities of others.
Right. And the source actually introduces propositional attitudes, like believes, knows, wants, and informs. What's the challenge in just treating those as regular predicates in, say, first-order logic?
So the issue is something called referential opacity.
Okay.
So with standard predicates, if two terms refer to the same object, you can substitute one for the other without changing the truth of a statement. But this doesn't work for propositional attitudes.
Okay.
So the classic example is Lois Lane knowing that Superman can fly, but not knowing that Clark Kent can fly, even though they are the same person. And standard logic would actually incorrectly infer that if Lois knows Superman can fly, and Superman is Clark Kent, then Lois knows Clark Kent can fly.
Okay, so how does modal logic offer a way to deal with this problem?
So modal logic introduces these special modal operators that take whole sentences as arguments,
Okay.
rather than just terms that refer to objects.
Hmm.
So for knowledge, we often use an operator like K. So Agent A knows P would be written as KAP.
Okay.
And this allows us to actually reason about the content of that knowledge or belief without running into those problems of referential transparency.
Okay, and then the underlying semantics of modal logic get a little bit more complex.
They do, yeah.
With this concept of possible worlds.
Right. So instead of just relying on a single, definitive true world, a modal logic model considers this collection of possible worlds.
Mhm.
And these worlds are connected by these accessibility relations, which are specific to each modal operator.
Okay.
So for example, a world W1 is considered accessible from 0, 0 with respect to what agent A knows if everything that's true in W1 is consistent with what A knows in W1. Then KAP is true in a world W if and only if P is true in every possible world that's accessible from W according to what A knows.
Hmm.
So this framework allows us to handle these different scenarios, like the fact that in some possible worlds, Lois Lane might not know that Clark Kent is Superman.
Right, and this helps clarify those, tricky issues with quantifiers in knowledge statements. Right? Like Bond knows that someone is a spy.
Exactly. So modal logic lets us distinguish between there is a specific person X that Bond knows is a spy.
Right.
And Bond knows that there exists at least one spy, but he may not know who it is.
Right.
And so the order of the quantifier, that's someone relative to the knowledge operator, the K, actually determines the meaning.
Okay. And then are there axioms that govern, how knowledge behaves within this modal logic framework?
Yeah, there are. So you have principles like closure under implication.
Okay.
So if you know P, and you know that P implies Q, then you also know Q.
Right.
There's the veridicality of knowledge.
Hmm.
So if you know P, then P must be true. And positive introspection.
Hmm.
So if you know P, then you know that you know P.
Okay.
And similar axioms exist for belief as well. However, modal logic also has to grapple with this problem of logical omniscience, which is this kind of unrealistic assumption that, if an agent knows all these axioms,
Right.
they automatically know all of the logical consequences of those axioms, which is, of course, not how things work in reality.
Right, exactly.
Yeah.
The source also mentions some other types of modal logic beyond those for knowledge and belief, including those related to time.
Right. So you have modal operators for things like possibility and necessity.
Okay.
And then linear temporal logic introduces these operators like X for next, F for eventually, G for always, and U for until, which we saw briefly in those sections we talked about earlier.
Right. And while those add a layer of complexity, they can actually provide much more concise and natural ways to represent